All right, so welcome to the 19th lecture of the STAT 313. Last time we studied the one-way ANOVA, and in fact, we spent last two classes describing the theory. So one class we described the theory, and the second class we described the application, or in terms of some solved problems. Okay. So today, what we are going to do is we are going to very briefly see a two-way ANOVA. And instead of doing too much theory, so we'll be simply doing some examples. Okay, so the theory is very similar to what we learned last time, except so this is for the case of two variables. I'll not go into theory. If you are interested, you can check the textbook, but it's similar. Instead, I'll show you how to compute this in practice. Okay, so let's get started. So today we are starting the two-way ANOVA. Okay. So first of all, let's see what's the difference between the one-way ANOVA that we learned before and two-way ANOVA that we are discussing in this section. So in general, so this one-way ANOVA or two-way ANOVA, so there are statistical tests that are used to compare the means across different groups. Okay, but they differ in the number of independent variables. So one-way ANOVA that we did before, so that uses one independent variable. So there are, so in the case of one-way ANOVA, as we have said, as we have seen, that one independent variable. And for two-way ANOVA, we have two independent variables. Okay. So in general, this one-way or two-way, the ANOVAs are statistical tests used to compare means across different groups. But they differ. So the procedure is the same, but they differ in the number of independent variables they analyze. So as I mentioned, that for the case of the one-way ANOVA, we have already seen that they analyze one variable. For the case of two-way ANOVA, we'll see that it's there are two independent variables. Okay. Now, just to give it a little more context. So today we'll be considering, so suppose that, so today I will be discussing the two-way ANOVA. So suppose that we have a random experiment. A random sample consisting of A times B observations. I'll explain what it means as we go along. Okay, which are classified according to two factors. Say into A classes. It's not A class, so it's a class into, so we'll see what it means, but A classes of factor A and into B classes of factor B. So there are two independent factors, A and B. So there are A number of classes of factor A and B number of classes of factor B. So this will be much more clear when we do an example, but at this point, this is sufficient. Also, there is a serious assumption we'll be making, which may be relaxed later and but we'll be not discussing that too much. We assume that there is one observation in each of I'm trying to fix my camera. Yeah. In each of AB cells. Okay, so let me just draw it here. So we have two factors. So the first factor, we wrote it as A, and it has A number of classes. So maybe it's A1, so factor, A2, A sub A, and the B1, it has B1, B2, B sub B. So you see that there are total A times B number of factors, and we'll label it as before. So it's X11, X12, X1A, X21, X22, X2A, XB1, XB2, XBA. Okay, so there is a total AB or BA number of cells. And we are assuming that corresponding to every cell, there is just one. So there is just one observation. Okay, so total cells AB, and corresponding to that, we are having one observation. Okay, corresponding to class of, so we call this one as the factors. So this is factor A, and simultaneously a class of factor B, meaning this picture. Okay. So this is a thing. So basically, it's really important. So let me just write. So there is one observation per cell. And what is cell? So these things are called cells per cell. Okay. Okay. I mean, of course, this can be relaxed. Now we'll try to model this. So our model will be the following. So we'll be writing this as xij would be, say, some mu plus alpha I plus beta j plus some e of ij. So this is a purely error term, where we'll call this mu to be the general effect we'll call alpha I is the effect special to ith class according to factor A. Okay, so and what is my I running from? So I is 1, 2, all the way up to A. Okay, so there are so for every column. So since they are from same factor, we'll see what it means. But since they are from so factor A, so they have a effect special to that. So that's something we called alpha I. And beta J, so this is the effect special to jth class according to factor B. So for example, here J is 1, 2, all the way up to B. So for example, you see is a beta sub 2. So that is a very special effect of this one. Okay, so for this row. So for the second factor, so for the second factor, so all this will have some effect. So that is given by that. And this EIJ will write this as the error component. And this model is called a linear model. So essentially what we are having is we are having alpha I values. So we have an effect from one of the first factors, or the first factor A, and then we have an effect from the second factor B. And then we have some error terms. So Xij, any observation, is made up of the sum of the effects of various components. So that's the linear model. Okay. So we assume that this is this Eij is independently for every Ij distributed normal random variables with mean 0 and variance sigma squared. Okay, assumption. Okay. And typically this sigma square is unknown. All right, so all we are assuming that they are with the same variance, the error is for same like having same variance sigma squared, but their mean is 0. Okay, that's the setup. Now with this, let's proceed. That's now. If we want to analyze, so in the two-way classified data, so the ANOVA may be used to decide one, so it will be deciding on two types of problems. And we'll do it simultaneously. Okay. The first one is whether the first type of problem is whether there is any differential effect due to classification by factor A. So in this case, the null hypothesis, we'll call it H0A or HOA, which is, we can, I mean, there are various ways of writing it, but I will write this in the following way. So we'll write this as alpha 1 equals to alpha 2 equals to all the way up to, by alpha, I mean this ones, okay? Equals to alpha A equals 0. So that means we are assuming that for factor, I mean, is there any differential ways of this? So whether there is a differential effect due to classification factor A. So if all these are 0, so that means that there is none. So there is no differential ways of this particular factor. Okay? So that means it doesn't really matter from which factor 8 comes from. It will be always the same. Okay? And here, what is the alternative hypothesis? So if you are testing this one, so it's versus H1A, which is alpha I is not equal to 0 for some I. That means there is a differential, I mean, so there is an effect of factor A. And the second one is, you can imagine that this is for the B. I'll write the same thing. Number 2 is whether there is any differential effect due to classification by factor B. Okay, so the first one was by factor A and this is by factor B. So here the null hypothesis would be H0B, which is all the betas, beta 1, beta 2, and we have B amount of those, so those are 0. And what we are doing is we are checking this against versus the alternative hypothesis H1B, which is beta sub j is not equal to 0 for some j. So that is the alternative hypothesis. That's what we are going to check. Okay. Now, the analysis with this setup, the analysis is very similar to what we have done before, except now we have just 2 components. Okay, so I'll not try to compute all those things. Instead, I'll be showing you a procedural way of doing this. So let's some notations. Okay, let's write say notations. Okay. First of all, we have already defined A and B, which are A is the number of factors in big A, the factor. So number of classes by factor big A is called little a, and number of classes by factor big B is called little b, right? Now I'll define N, which is equals to A times B. So it's the total number of observations. Okay. Now T sub I, so would be sorry, my table is a little bit flipped, so I should have really called this factor A here, but it doesn't really matter since. So Ti, when I use a notation, I'll be calling this the total of ith row. Okay, and so here I is 1, 2, A. So the picture, which is really I'll be using going forward. Let me just flip it a little bit, but let me just write first. And then I'll be using tj prime, which is given by total of the jth column. It's nothing serious, but I just want to be consistent. So let me just look my picture. So the picture is see picture on next page. What I'm meaning here is I'll be using the fact, it doesn't really matter, but I just want to make my notations consistent. So I'll write A here, B here. Okay. And the observations for A are A1, A2, all the way up to A sub A. And observations for B are B1, B2, all the way up to B sub B. Okay. So here the values, I'll write this x11, x12, x1b. That is more like in this notation. So let me just write here what I drew before. Let me delete this picture, okay? Because otherwise it will be very confusing. So let me just not use this picture. All right, see picture on, this is my page 4. Page 4. Okay, yeah, now it's much better. All right, so it's x11, x12, and now this is x21, x22, x2b, xa1, xa2, xab. Okay. Now what we are writing here is basically the total. So here, so we are denoting this by say T1. So this is my T1. Okay. So this is T1, this is T2, and this is TA. And here the totals are given by T1 prime because it's for the J index. So this is the I index, and here it's J index. T1 prime, T2 prime, T sub B prime. Okay, so that's the notation. Okay, that's it. And then I denote the T to be the grand total. So this is T of all observations. That can be obtained in 3 different ways. I can write this Ti, I from 1 to A, that is same as Ti prime, sorry, Tj prime, J from 1 to B, or I can write this as double summation, Xij, I from 1 to A, J from 1 to B. Okay, so that's T. Okay. Now I'll be writing Xi bar is the Ti over A so that means sorry, what I meant to say is so this is the mean for the ith column. For example, if I want to add this and divide, if I want to compute the mean for this one, so I have to write T1, so that the sum of this one is T1, and I have to divide by B. There are total B number of entries. Okay. So this is the mean for the ith row, And then I write xj bar, which is tj prime over a. So that is the mean for jth row or jth column. And x bar is the grand mean. So it's t over ab, which is same as t over n according to our notation. So it's the grand mean of all observations. So, okay. So what is the, for the every row, it has a mean. Every column, it has a mean. And then we have a grand mean. Okay. So these are the three quantities. Now, as I said, today will not be dealing too much with the theory, but just let me mention it here. So it can be shown that, and it's very similar to what we have done earlier, that summation I from 1 to a, j from 1 to b, xij minus x bar squared is equal to basically b times summation xi bar minus x bar squared, and I runs from 1 to a, plus a times the other sum, xj bar minus x bar squared, j runs from 1 to b, and plus double summation, and this is for I runs from 1 to a, j runs from 1 to b, xij minus xi bar minus xj bar minus x bar squared. It's a very simple computation that can be done. Okay. Now, the way we understand this is this quantity will write the total sum of squares. So this is this one. Okay. And if you recall, so this one is the sum of squares. So sum of squares, we denote it by SS, right? So this is xi is, so I is the factor a, right? So if we have different I values, so that means we are talking about different factors in a. So this is really SS between factor a, this quantity. Okay. This one is SS, sum of squares, between factor b. And finally, this quantity is the sum of squares due to error. Okay. So we write this as SS due to error. It's not really classified as A or B, it's just the error. Okay. This equation is sometimes written as, so this one is called the total SS, as I mentioned. This is called sum of squares between factors A, so it's written as SSA. Sum of squares of factors, it's called SSB. And this sum of squares due to error is called SSE. Okay. So total SS is this. Also, the degrees, so this equation is very important. The degrees, again, we didn't show the details of all the calculations like last time, but I think this is more or less understandable. So the degrees of freedom of various SS can be split up as well, meaning that so the degrees of freedom of total SS is really AB minus 1. Degrees of freedom of SSA is A minus 1. Degrees of freedom of SSB is B minus 1. And degrees of freedom of SSE is, in fact, it's A minus 1 times B minus 1. And what we're just claiming here also, note that this AB minus 1 can be written as A minus 1 plus B minus 1 plus A minus 1 times B minus 1. Okay. Okay. So that means this statement holds true. So sum of square, this relation is true, as well as this one is true. Okay. Now we can really think what we're going to do next based on the again, I'm not showing you all the details or theoretical details, but based on the analysis that we did for the one-way ANOVA, you can expect that the next one which we'll be computing is the mean square between classes, right? So mean square between classes of the A and B. So mean square are calculated as before. By dividing the sum of squares by the corresponding degrees of freedom. So for instance, the mean square between classes by factor A, which we call as MSA, which is really SSA by its corresponding degrees of freedom, that is A minus 1. Mean squared between classes by factor B, we write this as MSB, which is SSB over K minus 1. And finally, we write the mean square error. You must have seen it in the last ANOVA as well. It's MSE. It's basically SSE over this quantity, A minus B times B minus C. So this quantity, A minus 1 times B minus 1. Sorry, this is not K, this is B. Degrees of freedom of B in this case. Okay. Okay. So now the idea is we'll be computing two F1 scores. So the first one is when H0A is true, the statistic F1, which is given by, I think we're calling it FA. So FA, which is given by MSA over MSB, sorry, MSE. It follows the chi-square distribution with the degrees of freedom. Sorry, it follows an F distribution with the degrees of freedom. So for MSA, it's A minus 1, and the other one is A minus 1, B minus 1. Okay. And when the other one, namely H0B, is true, then the FB, which is MSB over MSE, it follows an F distribution with B minus 1 and A minus 1, B minus 1. It's very similar to what we have done earlier. And that's pretty much it. From there, we'll try to conclude things. Okay. All right. So that is pretty much all the ideas. Okay. Now, while doing the computation, you may, just like before, I'll give you some tricks of computing all these things. So, but all these kind of quantities are here. So let's now write it some of the techniques of computing this efficiently. So computational guide, you may say. So first of all, SSA, which is given by B times summation I from 1 to A xi bar minus x bar squared, it can be shown that this is given by summation Ti squared over B, I from 1 to A, minus T squared over N. First thing, SSB can be shown to compute. So SSB is given by summation A from A times summation J from 1 to B, xj minus xj squared. And we can show that this is given by summation Tj prime. So we have defined everything before. So remember what is Tj? So the Tj is right here. So we have all these definitions. So T, Ti, Tj. Okay, so these are all the notations that we used before. So this is Tj prime squared over A, and then J from 1 to B minus T squared over N. And also the total SS is given by summation I from 1 to N, I from 1 to A, J from 1 to B, xij squared minus T squared over N. So you see this factor T squared over N is coming a lot of times. So that's why it's sometimes called the correction factor. Okay, so it's called the correction factor because it just appears everywhere, T squared over N. And by the way, from this relation, what we already mentioned, by 1. So this relation is, let's call 1. By 1, therefore, we can write the SSE equals to total SS minus SSA minus SSB. Okay. That's it. So this is the procedure for calculation. In other words, I'm saying to you that there are nicer tricks for computing SSA, SSB, and then total SS. In effect, I can compute SSE by this. And from there, we'll be constructing the ANOVA table as before, and we'll be solving the problems. Okay, so that's it. So now let's see an example. So how this can be used in practice. So here is an example. So it goes like this. Three experimenters determine the moisture condition or the moisture content of samples of a product, say powder. Each of the experimenter is taking a sample, that means one sample, from each of 4 consignments. The results are given below. Okay, so here's the deal. So we'll call the experimenter and then the consignments here. So there are 4 consignments. So 1 class of powder, 2nd, 3rd, and 4th. And the experimenters will call it A, B, and C. And the numbers, they're taking a sample from each of the 4 consignments. So just one sample. So it's 9, 10, 9, 10, 12, 11, 9, 11, 11, 12, 10, 12. Okay. So the question is, perform an analysis of variance, an ANOVA, on this data and discuss whether there is any significant difference between consignments and or between experimenters. Okay. So that means, is there any difference between, it's actually or is a better word, because I'm just trying to compare between the experimenters or compare between the consignments. So is there any difference between these 4 products and the average? Or is there any effect of this one? So that's essentially captured by that quantity, remember, alpha sub, so beta sub j, and this is captured by alpha sub I. And so that's the thing. Okay, now this is a classic example of ANOVA. So let's solve this problem. So solution. So the way we'll solve it is, I mean, once again, this data set is not big, but I just want to show you, just like before, we can shift any number by anything that will not affect analysis of variance. Okay, because the shifting variance does not see the shifting. So I can shift this by anything I want. So let's shift. Next example, I'll do it without shifting, but I just want you to know that there's these options are available and you can reduce the numbers. So shift observations by 10. So new table becomes the following. I'll draw the same table. So we have consignment and then we have experimenter. So there are 4 consignments, 1, 2, 3, and 4. And then I have A, B, and C. So I'm basically replicating the previous table. So I'm just shift everything by, so this number 9 will be -1, this is 2, this is 1, so on. So it's -1, 2, 1, 0, 1, 2, -1, -1, 0, 0, 1, 2. So here shifting does not change anything in ANOVA analysis. The scaling does, but we're not doing scaling. But I think in the last class we have done one example in scaling where we actually got back to the original variables. Some I have shown you how to do it. But shifting is the best thing you can do. All right. So if we have this one, then let's compute the total. So let's write the totals here. Total, which we write as T sub I. Here it's -2. Or totals of this one is -2. 2 plus 1 minus 1, 1. It's 3. It's 5, which is called Ti. Okay. And then here, totals, which you call Tj prime, is a prime because otherwise it'll be we cannot distinguish between Ti and Tj when the numbers are given. So that's why the prime is used. So it's 2. So this number is 2. This number is 3 minus 2, 3. So the grand total is 6. Okay. Now, total of squares. So why do I need it? Remember that total of squares is needed, this quantity I'm talking about. So that is summation, in our case, I from 1 to 3, j from 1 to 4, xij squared. Basically, you're just squaring and adding everything. You'll get 18 in this case. Every cell, you just square and add. Okay. Now compute the t squared over n, which is the correction factor, which is so important, we have seen. So what is t squared over n? So that is basically 6 squared. And what is n? N is the total number of observations, which is 4 times 3, 12, right? So it's over 12. So it's 3. Therefore, total SS, which is summation I from 1 to 3, j from 1 to 4, xij squared minus t squared over n. So we have already computed this too. So it's 18 minus 3, so it's 15. That's the total SS. SSA, which is given by summation ti square over b, and b is really, so here my a is, so a is the number 3 and b is the 4. Okay. So it's ti square over 4, and I runs from 1 to 3. Okay. So that is the SSA. Or I think it's a, if I write SSA, it's confusing. So it's really the SS between the experimenters. So here, my factor A, I should write it here. So my factor A is the experimenter, and factor B is a consignment. All right. So SSA, or the sum of squares of between the experimenters. So that is going to be this quantity minus t squared over n. Right. If you compute this, so this is going to be 6.5. Can check. It's very easy computation. So all the TIs are given. So basically, this is T1, this is T2, this is T3, and this is T1 prime, this is T2 prime, this is T3 prime, this is T4 prime. I just compute this using this. Okay. Now, similarly, the SSB, which is the sum of squares between the consignments, which is given by summation j from 1 to 4 tj prime squared over 3 minus t squared over n. Okay. Now all the numbers are given. You can compute this. So this is really 5.67. From where I'm getting all these equations. So this is something which is written here. The computational way, I have listed everything which you need to know for computations. Okay. All right, so so we have SSA, we have total SS, and then we have SSB. So that means we can compute SSE. So SSE, which is the sum squares due to error, which is total SS minus SSA minus SSB. So which is 15 minus 6.5 minus 5.67. So we are just subtracting all these three numbers from 15. And what we get is 2.83. So that is the total SS. Sorry, it's SSE. Okay. Now let's draw an analysis of so ANOVA table. So ANOVA table. Yeah, I can compute, of course, the MSA, MSB. Let's do it in the analysis of variance table. So I'll write this in the following way. So source of variation. There are two different sources. Last time for the one-way ANOVA, it's just one. So here it's between the experimenters. That is the factor A. Or it can be between the consignments. That is the factor B. Okay, so two different sources of variations, and then the final one is the error. Simply error. Okay, so that is the SSE thing. Now we write the sum of squares. The first one, we have found that the sum of squares in factor A, so SSA. So if it helps, let me just show you this picture. So it's we did here. Okay, so I think we wrote DF first. So let's write DF first. So let's start with the DF. So the first case, what is the degrees of freedom here? So we know that for the experiment for the first one, so we have listed it here. It's A minus 1, right? So and A is so A is 3, so it's A minus 1, so it's 3 minus 1, which is 2. That's the degrees of freedom. Now for factor B, it's B minus 1, then B is 4, so 4 minus 1, which is 3. Okay, and error is actually it's A minus 1 times B minus 1. It's A minus 1, B minus 1. So it's really 6. Okay, so that is the degrees of freedom. Okay, and the total degrees of freedom, it's additive, so it's 11. That's the first one. Now, the next thing we did is the SS. So this is giving me SSA, which we already obtained to be 6.5. This is SSB, we already obtained to be 5.67. 6.5, 5.67. And this is SSE. We obtained this right here, 2.83. And also these are additive, so it's 15. So total sum of squares is 15. Now we'll write MS. So MSA, which is really SSA over A minus 1, right? So this is something we have, I have written at the very beginning. So when you compute the MSA, so this is SSA over A minus 1. If you compute this, so it's basically this number over 2. So it's 3.25. Okay. MSB, so this is SSB over B minus 1. So it's 5.67 divided by 3. So it's 1.89. And finally, MSE, which is SSE over A minus 1, B minus 1, the corresponding degrees of freedom. If you compute this number here, it's 0.47. And these are not additive, so I'll not write anything here. Okay. The structure should be very similar to what we have done for one-way ANOVA. Look at this. So this is the thing we did, and we are doing the exact same thing. So except now we have another factor. Okay. So now the F values. So let's compute the observed ones. And then I'll write the theoretical ones. Okay. So for the first one, when you compute the first, so FA is MSA over MSE, which is given by 6.91. And FB, which is MSB over MSE, which is 4.02. Corresponding value with significance level 0.5 for alpha equals to 0.05. F of 0.05, the tabulated value for the degrees of freedom. So here it's basically 2 and 6 is given by 5.14. And here with critical level or significance level 0.05 and the degrees of freedom 3 and 6 is given by 4.76. So note that we'll be comparing this with this one and this with this one. Okay. Okay, so what is the comparison? So of course, this number is more than this one, and this number is less than this one. Okay. So first of all, so the observed, so FA conclusion. FA is larger than the F critical value. So that means we reject the H0. And what was the H0A. Therefore, we conclude that the mean moisture content as determined by the three experimenters are not equal. Okay. So that means the mean moisture content as determined by three experimenters or different experimenters are not equal. So that is, there is a significant difference in the experimenters. There is a significant differences between the factor A experimenters. That is factor A. Okay. So that's the first thing, first observation. So that is what we get from here. What about the other one? For the other one, but if B is less than F 0.0536. So this was 4.07, this is 4.76. And therefore, it's not a significant 5% level difference. So we conclude, so that means we accept H0 or we fail to reject H0. So that means we conclude that the moisture content of different assignments or different consignments may not be different from one another. So, or in other words, that is, there is no significant differences between the consignments. Okay. All right. So that is how it's typically done. Okay. So now let's solve another example, which is just to reinforce this idea. This one example, it goes like this. The following data so what we're going to show now, the following data show the production of 4 workmen on 3 machines. So test whether those 3 workmen differ in respect to mean productivity. Okay. So now we are really not really concerned with the well, we can compute this for both workers and machines. So let me just change this problem to do the same for the machines. Okay, let's do that. So we are trying to see if there is a productivity differs according to the workman or machines. Okay. So there is some data. So here is a machine, and here is a workman, the person who is running the machine, A, B, C. And here's machine number 1, machine number 2, machine number 3. Okay. What are the information given? So here it's a 38, 36, 49, 33, 44, 42, 46, 42, 39. Okay, so these are the numbers which are given. Okay, so here basically we are saying the factor A is the machine, factor B is the workman. So let's solve this, the solution. So in this case, my factor A is the machine and factor B is the workman. Okay. Let's now draw the table. So one more time. So this is the workman, and here is the machine. We have A, B, C, A, B, and C. And we have machine number 1, 2, and 3. Okay, so once again, let's just write it. 38, 33, 46, 36, 44, 42, 49, 42, 39. Okay. Now, for a change, so for this problem, again, if you want, you can just shift everything by, say, 35, and you can do it. But just for showing you that that's not really a necessary step, so you can even do it with the, I mean, if you can use a calculator to compute this, that's perfectly fine. So you don't need those shift all the time, okay? You don't need those shift any time, but we use those shift so that we can handle with the smaller numbers. But here we'll just stick to the bigger numbers to see how it goes, okay? So here, total TI. So we'll be computing all these totals, okay? So let's add up all these quantities. So the first one is 117, which is my T1. The second one is 130 if I add all these three. So that's my T2. And if I add this three, I'll get this number is 117, this is 122. 122, and this is 130. So that is 33. Okay, and now what about the others here? So total in TJ prime. So if I add this three, I'll get 119, which is really T1 prime. So this number, if I add, it's 127, which is really T2 prime. And if I add these three numbers, I'll get, sorry, it's 11. This number is, sorry about that. So it's 123. So this number here, let me make it up here. So this number is 123, 119, and this number here is 127. So this is really T1 prime, this is T2 prime, and this is T3 prime. Now, if you add everything, so this is 369. So that is my grand total T. Once again, you see that in the last example, we had much smaller numbers, but here we are having pretty big numbers, right? So let's compute all those quantities, say total sum of squares or total of squares, whatever we call, which is given by really, we have I from 1 to, so here in this example, A equals to 3, B equals to 3, right? So N is 9. N is A times B, which is 9. Okay, I from 1 to 3, J from 1 to 3, Xij squared. So let's compute. Okay, so just replicate the computation as we have done before. So we have found the total sum of square. So we have found the total of the squares, right? So let's compute the correction factor too. So correction factor that we have defined as t squared over n, right? So this is t squared means 369 squared over 9, which is 15129. All right, so now let's compute the total SS, just like the last problem. So total SS is really summation I from 1 to 3, summation j from 1 to 3, xij squared minus t squared over n. By the way, so total sum of squares, so this sum of squares, did I compute this? No, it seems like I didn't compute it. So let's do it. So this number is here 15331. It's a big number because remember, that's the advantage of reducing those numbers. So then you would get a smaller number here. All right, so this one is 15331 minus 15129, which is 202. Okay, so that's the total sum of squares. Now SSA, my A is the machine. So this is SS between machines, which is given by summation TI squared over, so now how many numbers we have? We have 3. So we have I from 1 to 3, and so both A and B are 3 here. So it's minus t squared over n. If you compute this, so you can compute this from this T1, T2, and T3, right? So this quantity is really 15157.67 minus, we have already computed this, it's 15129. So once again, it's a big number. So this is, if I compute this, it's 28.67. Okay. So that is SSA. Let's move on and compute SSB. So we have SSB, and this is the SS between the workmen, which is given by summation tj prime squared over 3 and j from 1 to 3. Here A is 3 and B is also 3 minus t squared over n. If you compute this quantity, so this is going to be 15139.67 minus, this is as before, 15129. So if you compute this, it's 28.62. Okay. So that is SSB. And what is SSE? Just like before, we have seen this. So so we have computed the SSA and SSB. And from there, we can compute the SSE. So SSE is just by equation number 1 that we have seen before. So it's a total SS minus SSA minus SSB, which in our case, if we compute this, it's going to be 162.67. So that is SSE. Okay, so we get all the numbers. So now let's put this in the table. So the ANOVA table will have the following. So we have source of variation. So the first one is between machines. That is my factor A. The second one is between the workmen. That is factor B. And finally, we have error. Okay. Let's write the degrees of freedom. So the degrees of freedom, here is 2. Here is 2. A minus 1 is, so 3 minus 1, 2, 3 minus 1, 2. And this is A minus 1 times B minus 1. So in this case, the degrees of freedom will be 4, right? So this is 4. Okay. All right, so we found the degrees of freedom. So now the total also I can write. The total of degrees of freedom is 8. Right? Now SS. We have SSA. So we have already computed SSA. So let's just plug the value here. So SSA we found 28.67. SSB we found it 28.62. I think it's not 28. It's I think there's some mistake in the calculation. This should be around 10. So it's 10.67. So the first one is 28.67. The second one is 10.67. Okay. So this number is 10.67. Okay, it's 139 and 129. And then finally we have some SSE, which we computed to be 162.67. Okay. And the total, they add up. So total was 202. So it's approximately 202. I mean, yeah, so we are approximating. Done. Next is the MS. So what is MSA? So MSA is SSA over 2, right? Degrees of freedom was 2. So if I compute the MSA over 2, so that is going to be 14.33. MSB is SSB over 2 again. So that is going to be 5.33. And finally, MSE, which is SSE over 4. So that means this number divided 4, it's about 40.67. And we don't add here. Okay. That's pretty much it. And now we are ready to write our F values. So observed and theoretical. So FA, so FA is, as we have seen before, it's MSA over MSE. So this number divided by this number. If you compute it, it's about 0.3525. FB is MSB over MSE. So 5.33 over 40.67. So it's about 0.1311. So these are the values that you're getting. Now the tabulated values, you can check it with, say, alpha value equals to 0.05, f of 0.05 with the degrees of freedom 2 and 4. So that is given by 6.94. That's the comparison for this two. And also for this one, it's f of 0.05 and degrees of freedom are 2 and, sorry, this 2 and 4. So incidentally, they are the same here, but in many problems, they will be different because here the degrees of freedom is taken from MSB. And so it's usually this one. So here they are both 2. So we are having the same number, but we may not be that lucky for all the problems. So this is what we get. Okay. So we have all these values which we found. Okay. Okay. So now, therefore, now we are ready to conclude. So conclusion, we observe that the observed value is always less than the theoretical values, right? So FA is less than F 0.05 with appropriate degrees of freedom, that is 2, 4. And also FB is less than 0.05 appropriate degrees of freedom. So that means we cannot reject H0, or we'll keep H0 A. And here we cannot reject H0 A B. Okay, so that means we'll conclude that neither workmen nor machines let me just write it in another way. It's a very lousy way of writing. So let me just write the conclusion. So that means there is no significance difference between with respect to workmen on mean productivity. And also there is, so this is for factor B, and there is no significance difference with respect to machines on mean productivity. Okay, so that's the conclusion. So this is typically how it works. So this analysis of variance, so when you have multiple factors, this is how this analysis of variance can be implemented for analyzing those factors. Okay. So this is all about ANOVA. So as you have seen that today we have approached this from an experimental point of view, so that we solve problems rather than going too much into the theory. So next time, so this is all about the ANOVA we want to talk about. So last 2 classes we have done one-way ANOVA, and today we have done a 2-way ANOVA. So next time we'll be starting something new, which is linear regression. Okay. So thank you very much.